everybody. So I'm Marina. I'm going to talk today about container isolation for secure multi-tenancy. So first, a little bit about me. I work at a company called Adera, which is like a cloud-native hypervisor for isolating your containers and GPUs. And what I do there is I'm a research scientist and head of Adera research. So I get to look at cool new technologies in this space and how they all fit together. I'm also a co-chair of the group formerly known as Tag Security in the CNCF, as well as doing some other work on open source projects. We'll skip past that. So let's start with the problem. So in multi-tenant environments, multiple applications belonging to multiple users are sharing an environment, right? And so these users might be different customers of a company running the same application, or applications from multiple different companies or customers sharing the infrastructure for cost savings, for efficiency. Yeah, and more specifically, because we're talking about Kubernetes, these applications are containers. So we're going to call them containers from here on out. And the shared infrastructure they share is a kernel, right? They're all using the same kernel, the same address space. And what this means in practice is that, unfortunately, it's very common for applications to be able to read or alter data from other applications, sometimes known as a container escape. And what we need is some form of isolation to prevent these applications from interfering with each other, especially in these multi-tenant environments when these containers aren't all run by the same people. And so there's a lot of tools out there in the world that help with isolation. We're going to talk about a bunch of open source tools in this talk, kind of focusing on the open source space, and break them broadly into three categories: no isolation, weak isolation, and strong isolation. So strong isolation has no shared kernel space between containers. That's how we're going to define it today. This means no shared kernel, no shared address space. Weak isolation still provides some isolation between the containers, but it doesn't have a fully separate kernel and address space for each of them. And no isolation is what you have when you don't have any of these different protections. Of course, when deploying an application, isolation isn't the only concern. Right? I think in a lot of security talks, we focus so much on how to make something optimally secure that we don't really think about all the other factors you're thinking about when running your application. So other concerns might include things like performance of the application and the cost associated with running it, hardware requirements, the cost associated with those, and compatibility with the existing workloads and tools and kind of the development effort it will take. Each of these factors may be more or less important, depending on how sensitive the application is, what environment it's running in, whether it's multi-tenant, and more. And so even these solutions that provide no isolation might actually be perfectly fine if you control every application in the environment and stuff like that. There it is. So first we'll talk about some of these weak isolation features. Specifically, we'll start with some Linux kernel features in this somewhat overwhelming slide. Things like namespaces, cgroups, seccomp, capabilities, SE-Linux. Very broadly and quickly, these features create groups of resources or permissions for each container. And because they're all features of the kernel, in our kind of definition, they provide a form of weak isolation. And as we've seen in several different attacks in the past, some kind of kernel, because they share the kernel, if there's some sort of kernel exploit, this can very frequently lead to a container escape that violates these isolation protections even when these things are in place. Next, we have gvisor, which is a container sandbox that provides a user space application kernel, providing an extra layer of protection between containers and the underlying shared kernel. While this is able to prevent many known attacks on isolation, right, it provides this very strong barrier, there's still that underlying shared kernel between these containers. And this falls kind of between our definitions of weak and strong isolation, right? But because there's a shared kernel, we'll call it weak isolation by our definition. It's the problem with any categorization system. So in summary, there's a bunch of solutions that provide what we'll call weak isolation. And these isolation technologies, especially all those kernel features, can definitely be used in combination, right, to provide layers of protection. And even though they all have that shared kernel, this is sufficient for a lot of applications and environments, especially when things like performance are really important for your applications, and you're able to respond quickly in the event of some sort of kernel exploit. So before I start talking about strong isolation, kind of the next half of the talk, I want to kind of take a step back and start with a few definitions, because I think the space around hypervisors can scare people sometimes, and I'm hoping taking a step back will make it less scary. So you might have heard of virtual machines or hypervisors before. But I'm talking about the 3 components you actually need to run a container in like a virtual machine. And some folks refer to different pieces of this as a hypervisor. This is the definitions I'm using. And so, the bottom layer, is from the technology stack perspective, is the hypervisor. And what the hypervisor does is it partitions resources between different virtual machines. So it deals with the hardware, basically. And then you have a virtual machine monitor known as a VMM that orchestrates the virtual machines, right? It actually starts the virtual machines, it stops them, it sends resources to them. And then finally, because we're running containers, you need a container runtime that's able to run on the virtual machine that kind of provides a familiar environment for those containers, so they can just run. So like your existing containers can just run without you having to rewrite them. So I'm going to go through kind of each of those layers, and then we'll bring it all together. So in the open source world, there are 2 most popular hypervisors, are KVM and Zen. KVM is basically a module that uses the Linux kernel as the hypervisor. So it's basically part of the Linux kernel. It uses something known as hardware virtualization extensions that allows for kind of faster hardware-like emulation in the VMs. And these extensions are available on most modern CPUs, but in the cloud, you have to make sure it's a cloud instance that supports nested virtualization, so it can actually access the hardware kind of directly. And then there's Zen, which it's kind of a microkernel hypervisor. It's its own kind of code rather than being built on Linux. It uses something called para-virtualization, which is a little bit different. This means that the guest OSs, the OSs running inside the VMs, they need to be aware that they're running on a hypervisor. This means it doesn't have to do all of the hardware emulation that other hypervisors have to do, and also that it doesn't rely on these virtualization extensions. And that's partly just because it was written before they existed. So on top of this hypervisors, we have VMMs. This is a few open source examples. The ones on the slide are mostly ones that are built on top of KVM. For Zen, DOM0 you can kind of think of as the VMM. This is kind of I think they call it the orchestration domain, or the base domain for Zen. It does the same thing, where it orchestrates the different virtual machines built on top of it. And then, of course, you have a container runtime, so you can run the containers. Here's a few running out of time. And so one way to get strong isolation is to run your applications in virtual machines by choosing some combination of these layers, right? And so together, some people call this whole thing a hypervisor, but I think it's worth breaking down where the technologies fall. And any of these, of course, have a separate kernel for each container, so strong isolation. Not all these combinations actually work out of the box, and there's lots of folks, like my employer, that kind of work in this space to make this easier to actually use, but all these open source tools I have on these slides, of course, can also be used. Very quickly, another couple options for strong isolation. Another is a unikernel. Unikernel compiles the application along with the kernel into kind of I'll call it a mini operating system application thing. And this does also provide strong isolation, because each application, of course, has the kernel. But there's some limitations in terms of compatibility and development with this model. And finally, I'll very briefly mention confidential computing, which also, of course, provides very strong isolation, kind of hardware-based strong isolation, by running each container in a TEE, or trusted execution environment. In practice, this is often combined with a hypervisor to contain the application inside the TEE. And I think a couple projects in this space include like confidential containers or Constellation that make this work in the cloud-native space. So yeah, in summary, strong isolation means no shared kernel state, but it does come with a few trade-offs in a lot of cases, where sometimes you need these hardware requirements, especially for things like confidential computing, specialized chips, and sometimes there's the performance and compatibility of all these different technologies varies a lot, and you have to kind of put it together yourself. So finally, let's work together to prevent the next container escape from impacting multi-tenant applications by making isolation better. So if you're interested in any of this, or think I missed some interesting open source technologies and want to chat more about it, come talk to me. I'm interested in kind of getting us all together and talking more about this, and creating some sort of white paper industry group to make isolation better for everybody. So thank you. And I hope to get some questions.